Hey everyone! Quick heads up, you're watching the first episode of a brand new series I'm calling Katie's Lab. Most of my videos are project builds, silly ideas, or can I make this work chaos, but this series is different. This one is strictly reserved for genuinely new, industry-changing tech that's only just landed in the hands of makers. Stuff that adds brand new superpowers nobody at home has ever had before. Usually with these sorts of developments, it's valuable to actually spend some time understanding how they actually work. So whether next-gen lasers, automatic tool changes, crazy new printers, when something arrives that rewrites what's possible, it'll come straight to the lab for proper, no-holds-barred testing. So buckle up and welcome to Katie's Lab number 1, where we're testing an impossible laser. Every laser I've ever used burns. It scorches, melts, vaporizes, and that's literally how they work. But this one doesn't. This is the xTool F2 Ultra UV, a laser so precise it can engrave not just glass, but inside glass, mark metal without heat, and even write on chocolate without melting it. At many levels, this doesn't make sense, and to actually understand it, we've got to look at the atomic level. There is no better candidate for a proper lab investigation. Now, most lasers are pretty simple, really. They dump enormous amounts of focused heat onto a surface until it just gives up and burns away into soot. So diodes are great for the basic easy burn stuff like wood, paper, and the rest. Fibre lasers operate at a different wavelength, so they can tackle higher temperature materials like stones and metals. But this works differently. It doesn't use heat as such, it uses energy. The kind of light that can break the actual molecular bonds of materials directly. It operates in a strange world of photochemical reaction that allows some truly amazing results. Today, there's a few attributes I want to test so that we can understand more about exactly how it works. What makes ultraviolet light so powerful and flexible? So let's begin the experiment. Fetch the shiny things, chocolate bars, and tissues. It's lab time. Light looks so simple, but it hides something wild. Each colour of light carries a different amount of energy. So red light is gentle, blue light was a bit punchier. But beyond this is the really interesting part that goes beyond what the human eye can see. The ultraviolet range. All my other lasers, whether diode, fibre or CO2, work essentially the same way, heat. The light hits the surface, the atoms start vibrating, and eventually they give up and vaporize. You essentially cook your design onto the surface. And this is great, but it does mean that you are constantly fighting, trying to control the burn. Burning the bit you want whilst preserving the bits that you don't. But if you move the wavelength enough, you enter a different world. So listen up, you Planck. This is Planck's equation that you might recognise from school. What this tells us is that as you shorten the wavelength, you increase the energy of each photon. So if we could shorten the wavelength enough, we would be able to have enough electrons to start actually snapping the chemical bonds in materials rather than just burning them. And how far do we need to go? Well, about 355 nanometers works great, the wavelength of UV light. So while a traditional laser melts or burns, a UV laser changes the chemistry of the material itself. This is called photochemical ablation, which is just a fancy way of saying the photons are energetic enough to break molecular bonds directly. No heat zone, no char marks, just microscopic material disappearing one molecule at a time. Therefore, a laser operating at the UV range will be able to engrave things that other lasers just can't. So even though this looks very similar aesthetically, it's a totally different type of device. This doesn't burn materials, it sort of unmakes it. So that's the theory, but now let's actually test it. So here's the laser gauntlet, a lineup of materials suggested by my Patreons and YouTube members that basically covers everything that you might want to engrave, and a few things you definitely shouldn't. I want to test 4 key categories. How far can we push the precision of this device? How broad can it go on materials? How does it perform on super heat sensitive materials? And if it can etch super well, how does it do on carving without the ability to burn away layers? So lab coat on. Sorry, my mother is a retired chemistry teacher and we do this out of principle when testing. Lasers primed, and I've always wanted to say this, fire the lasers. These are some of the most exciting results I've seen in ages. I'll try and go through them logically, but there's some that I'm just itching to show you. Precision. Okay, lasers are great. They vastly outstrip the accuracy of devices like 3D printers, but this is seriously silly. I mean, look. Okay, let's try with a macro lens. Okay, let's get a microscope. This is like a different dimension. I am scanning a 3mm sized QR code through my phone and it works. Material flexibility. So a massive tick to precision. This alone has me excited. But precision is often not just about the actual dot size of the laser. Even if a laser can get into a particular level of detail, then if it's charring or warping the material itself, then this may blur or distort the result. This toothpick was very interesting to me, not just for the detail, but the lack of burn. Naturally, this leads us to material flexibility, and here's some of the results for etching. Wood. CO2 burns, diodes scorch, UV sort of draws. It's shallow, ultra-controlled, and has none of that usual burn halo at all. It feels almost printed. Where it's often hard with a laser to get the balance between detailed and broad spaces without charring, this just seems to work consistently regardless. Metal. Now, fibre must still win here in terms of pure suitability of wavelength, but I was actually pretty surprised here. I thought that UV may struggle with reflective surfaces like stainless steel, but you get that top-tier precision, no heat halo, permanent etching, and there's no way this would carve, but it's a pretty credible contender. Now plastics. These are the ones that I've always been annoyed with lasers over. They're often unpredictable. You can even get a cheap diode to mark certain colours and types of plastic. Like black PLA works okay, but white PLA does nothing, and it's a mixed bag of colours in between. Then, of course, hitting low temperature plastics with a burning hot laser is something that needs lots of careful tuning, and probably not something I'd trust myself with on a more expensive item. But we have so many plastic items around the house. It's kind of a big gap to be limited here. UV lasers, well, they don't give a hoot what you're fiddling with. They just work. This is one of the coolest things. They just seem to react with the pigment and pick the right result. They don't melt the plastic, they just change the pigment. If it's black plastic, they turn light. If it's light plastic, they turn dark. So every single colour worked. In fact, these etchings on Bamboo Lab swatch set that covers their complete colour range, looks strikingly familiar. I think I've worked out how they did that now. And it's a very good example of how these particular lasers pair very, very nicely with 3D printing enthusiasts. They'll fill the gaps of FDM printers in their ability to achieve tiny detail levels. Leather. Now, leather works on just about every laser in some form. Diodes sort of brand leather, CO2 will char it, but UV, this is actually great for what you can't see. You get none of that soot which screws up your design as it gets everywhere. Trust me, I know. It also lacks that burnt leather smell. It's just pretty neat. And the same applies to all the other fabrics I tried, like denim and microfiber cloth. It was great. Glass. This is the glass laser, no question. Where diode just passes through and CO2 sort of microfractures the surface, UV is perfect. The silica absorbs the 355 nanometer wavelength and it creates this lovely frosted finish. That with the precision, there's just no contest at all here. But I haven't scratched the surface here, or rather, I have. But I'll come back to this as it needs its own section. It's so cool. Then I was musing about the no heat effect, so I thought I'd test with food. I've etched biscuits before with lasers, but it takes quite a while to dial in the settings. But again, this is very different. Chocolate marks without melting or burning. Apples, bananas, pretty much everything. One interesting failure is really high sugar items, things that are basically pure sugar like marshmallows. These actually blackened very quickly, and I'm pretty sure that that's due to the chemical properties of sugar, much like it suddenly flips in the pan from heating to burnt if you're making caramel. I could probably tune this in to get better results, but that's an area that needs a bit more testing. All the other foodstuffs were very easy indeed to mark without issue, and taste wasn't affected at all. I know, I tested it. Heat-safe etching. Next, I wanted to test these much bigger margins on heat. This is immediately obvious when you etch silly items like a tissue. Naturally, that's extremely flammable, but this just etched and ultimately cut through quite happily. Again, without any scorching, char, or the rest. Likewise, chocolate under the microscope showed no signs of charring at all. It's just edible photochemistry. Test. But I think that there are far more obvious use cases for this where heat really does matter. And the most obvious thing is something like a microchip. I think you'd have to be mad to fire lasers at this normally, but this works amazingly. You can etch tiny details onto your chips or your circuits, anything, and it just works. There's a load of places that this could be useful. But also, this is neat for organic substances like wood. Now, most diodes and CO2s can easily cut wood, but I've never been a fan of the fact that you're burning through. All the edges end up charred and sooty and a bit frazzled. So it definitely limits where you can use it, whereas this gets very interesting. Embossing and carving. So this took me straight onto pushing the envelope. If I could etch one layer without char, could I do more? Can I carve with chemistry? Does that even work? Well, look at this. I have done nothing whatsoever to this. No sanding, no dusting. This is straight off the laser. It's like it's been CNC'd, but at the micron level. I have never seen anything even close to this before without post-processing and a lot of sanding. This is beautiful. It's just peeling off layer after layer without any burn whatsoever. So naturally, I had to go back to some chocolate, and sure enough, the same happens. 3D chocolate carvings are here, and still no taste change. Tested. Ceramic. Well, this was very nice indeed. Just look at this. Super crisp detail, No cracking or flaking or anything. Acrylics. Now here's a failure. Barada asked me to test out acrylics. Now I started out with black acrylic. You can see I was messing about with the settings to see if I can tune it in. And I can see with this one, so etching acrylic is a piece of cake with any colour or transparency. But cutting is possible, but with a bit of careful effort. But transparent is a total failure for me so far. You can see the acrylic is reacting and bubbling, meaning it's not removing anything. Rather, it's like a chemical boil happening. So I don't think this is possible, but shout below if you have any other ideas. But in summary, precision is a country mile ahead of all the other lasers. This sits around 100 times tighter spot than a standard CO2, and it shows. Material flexibility. This is easily the broadest range I've ever used with a laser. Heat-safe etching. Definitely. Now, I'm not saying you can't heat an object at all. If you keep pumping tons of energy in, of course it'll eventually heat, even chemically. But it's a totally different beast to any other laser. You can even feel this when you're dialing in settings. It seems to have a much bigger margin for error on everything. And carving? Well, this was a total surprise. It's amazing at three-dimensional work. And wood is something I'll definitely be using on my projects. Oh, and I haven't even shown you the party piece yet. Put this together. xTool have added the ability to etch glass at bonkers precision. They've then added the ability to shift the target layer automatically in the F2 range, moving layer by layer. It's almost like a 3D printer, although at 15,000 millimeters per second. Take that, Voron. So if you apply this to glass, yes, you got it. Let's take this STL file from MakerWorld, import it, and fire away. 20 minutes later, 3D print inside glass at micron precision. Cool or what? Finally, let's put this together, as I think you're going to see me using this lots in future projects. When I'm making electronics projects, I can now etch the device name on the device, mark the circuit, chips, add buttons to the case itself and helpful text. I can even add QR codes to link to the original manuals. Add serial numbers, icons, safety labels, or calibration marks at production quality. When I'm working with glass, this is now the only laser that I'll use. It's just a different dimension of production quality, but I'm thinking of all the cool projects I could integrate glass into now. 3D internal etches look great on their own, but even cooler with a light. So I need to brainstorm this. And my woodworking projects, I wasn't expecting that at all. This is awesome. Oh, and you want to know the single biggest bugbear in humankind? USB cables. Look at this. It doesn't care if your cable is metal or white plastic or black plastic or pink. It just works. So I can plug it in and etch the actual cable specs forever. They've obviously used a UV laser to etch their brand on one side. They could literally just have turned it over and put something actually useful on the other. Anyway, I'm going to sit and etch every cable with my trusty USB cable tester and never suffer again. Now, a quick note for anyone planning to get one of these. Even though it's cold marking, it still generates vapor. Like on paint, it'll be generating a chemical haze. So as always, ventilation still is essential. Don't scrimp. Likewise, just because the beam is invisible, it doesn't mean that you don't need protection. So shielding and or eye protection is essential. I'd better bring this test to an end. I could play with this all week, really. And to be clear, it's not a one fix solution that makes every other laser redundant. It won't cut thick stuff, but for that insane precision, clarity, and scientific literal cool factor, nothing else comes close. And if you like 3D printing, maybe this is the next tool you get to complement it. Can you see now why I'm so excited about UV lasers breaking into the mainstream? Lasers inspire assumptions that things are burning, but this is more of a photon sculptor. Less about power and more about control. Now, I haven't scratched the surface of all the features of this device, so I'll cover that in an upcoming video, so I can show off some of the impressive features that xTool have added, like the ability to generate 3D models from 2D photos, and the brand new next generation rotary that they've also launched with this, and the extra high-res cameras and much more. Plus, I still have even more things that I want to get creative with on this, like etching intricate glass jewellery. Comment on the weirdest material you'd like me to test next, and I'll try it in the next episode. I even tried a bubble. It didn't work. If you're curious about the xTool F2 UV, I will link to it in the description. I've actually realised that I've seen the work of UV lasers for years, and you can recognise that ultra-fine precision marking all over the place once you've used one. It's just that they've been stuck in big factories, semiconductor fabs, medical facilities and the rest. If you look at electronics, tools or devices around the home, there's every chance that you're staring at a UV laser's handiwork. The difference is that these previous huge and expensive capabilities are starting to enter the home, and nanotechnology in the home, well, that's very, very exciting. Right, test over. I've unfortunately ended with about a dozen new projects that I want to do. Huge thanks to all of my wonderful Patreons and YouTube members who fuel all of my experiments that usually end in smoke. And thanks to xTool who sent me this device to test even before it was available. But they know I'd just sit outside their HQ and annoy them until they relented otherwise. So they're very wise in that respect. We're vowed.
Where the chocolate melts and the microchips burn, and every new gadget starts worrying about its turn, 'cause she keeps prodding things she probably shouldn't just